So today my presentation is on a simulation of Brayton cycle in DWSIM. DWSIM is an open access chemical process simulation software. So in this video, we are going to see the simulation of Brayton cycle in DWSIM. So before going into DWSIM, so we will see the brief overview of Brayton cycle. So here the Brayton cycle starts at the stream 1, in which the fresh air enters at atmospheric temperature and pressure, and it is compressed in a multi-stage axial flow compressor where the pressure and temperature are increased, and it is sent to the combustion chamber. In combustion chamber, along with compressed air, the compressed natural gas as a fuel is also sent, where both burn together and produce gaseous mixture at high temperature and pressure. And this high temperature and pressure gaseous mixture is used to run the gas turbine from which the power is generated. So as I told you in the previous video, so some part of the turbine is used to run the compressor also. So that the compressor turbine are connected through a shaft. Okay, so whatever the power it is generated by the turbine, it is used for the compressor to run, as well as it is used for generating the power. And once the turbine used the high temperature and pressure hot gases from combustion chamber, then the exhaust is sent out of the turbine, which is having lower temperature when compared with the stream 3. So here, if you see, there are three main processes are taking place in Brayton cycle. Number one is compression. So here the compression is isentropic process. That means the process is constant entropy. Okay. And the pressure is increasing and the temperature is increasing. Okay. So in compression, entropy is constant, pressure and temperature are increasing. Okay. And in combustion, the process is isobaric. Okay, which means that the temperature is increasing, entropy is changing, but pressure is remain constant. Okay. And from the stream between 3 to 4, which is called as expansion. So during this process, the temperature decreases, pressure decreases, and entropy becomes constant. So the process from one compression and expansion are isentropic, and the process in combustion is isobaric. Okay, right. So with this introduction, actually I told you the compressor used here is multi-stage axial flow compressor, and the combustion chamber used is annular combustor, and the turbine used here is gas turbine. Okay. So with this introduction, let me go to DWSIM. So you go to Google and type DWSIM 8.4.1. Okay, actually the current version of DWSIM is 9.0.2, but this Brayton cycle simulation requires some salient features from DWSIM 8.4.1. Okay, so for successful simulation of Brayton cycle, you have to use only DWSIM 8.4.1. Okay, so if you click DWSIM 8.4.1, then you have to click on this SourceForge. Okay, the SourceForge link you have to click, and Actually, whatever I am telling you now, this is for Windows version. Okay, those who are using Windows. Okay, so then next after that you have to click on DWSIM Win V841 setup Win 7, Win 8, Win 10, V11, 64-bit exe. Okay, if you click, then the installer file will download, and once the installer file is downloaded, then you have to install it, and after the installation you will get two shortcuts in desktop. Okay, one is DWSIM cross platform and another one is DWSIM. Okay, so here you have to click on DWSIM. You have to click on DWSIM. Okay, so now you are seeing DWSIM version 8.4.1 is open. Okay, so you will not get this window. Okay, so now, so after you click on DWSIM, you will get this window. Okay, the update available. Okay, here it will ask you to update to the current version of DWSIM, but you should not do. Actually, as I told you, this DWSIM 8.4.1 has some additional features for Brayton cycle. Okay, so here you have to click on cancel. Okay, then later on, you have to click on create new. You have to click on create new. When you click on create new, this window will appear. Okay, so here click on next, and here you have to choose the chemicals that are involved in this Brayton cycle. Okay, so the first compound is air. You know there are two major components in air, that is nitrogen and oxygen. So I am going to add nitrogen and oxygen. Okay, so I am typing nitrogen. So the compound, the nitrogen is appearing. So here on the left hand side, you have to click on this checkbox. Okay, so then after this, you have to search for oxygen. Okay, so now air is done. Okay, after air, the next compound is natural gas. So natural gas contains methane. Natural gas contains methane. So you have to click on methane, and I am assuming that the natural gas contains methane and carbon dioxide. Okay. So next I am selecting carbon dioxide. Okay. And you know very well, after the combustion of natural gas with the air, it produces carbon dioxide and steam. Okay. So already we have added carbon dioxide. So no need to add it again. So now you have to add steam. So here in DWSIM, steam is not available. So instead of that, you have to add water. Okay. You have to add water. Okay, now make sure 5 components are added here. Okay, nitrogen, oxygen, methane, carbon dioxide, and water. Okay, now click next. So after this, now here you have to select the thermodynamic package. Okay, here you have to select the thermodynamic package. The Peng Robinson PR is the most suitable thermodynamic package for Brayton cycle. Okay, so after you click on Peng Robinson PR on the left hand side, you have to click add and make sure that Peng Robinson is appearing on the right hand side. Okay, so next, click next, and here, so you click on, so yes, we are not going to use the SI system. Okay, so you can use any one, either from C1 to C5. Okay, C1 to C5 is customized unit. Okay, we are going to customize the unit. So after you select either C1 or C2 or C3 or C4 or C5, you have to change this kg per hour to kg per second. You have to change this mass flow rate from kg per hour to kg per second. Later on, you directly go to pressure. In pressure, you select ATM. Okay, then energy flow, you select megawatt. In energy flow, you select megawatt. You have to make these 3 changes. Okay, mass flow rate, you have to change to kg per second. Pressure, you have to change to ATM, and energy flow, you have to change to megawatt. Then click on next and click on finish. Okay. So now what you have to do, now the DWSIM is open for you. Okay. Now the DWSIM is open for you. Okay. So the first component of the Brayton cycle we have seen as compressor. Okay. Now you have to introduce compressor. Okay. The compressor, if you see that at the bottom, there are so many menus are available. Okay. So here the compressor is available in pressure changer. Okay. So click on pressure changers and click on compressor. So drag it and paste it here. Okay. So drag it and place it in the DWSIM. Okay. So here you have, so this compressor has two material streams, 1 and 2, and one energy stream, which is E1. Okay. Okay. So two material streams, 1 and 2, and one energy stream. Okay. So here you click on C1. So you have to change the names. Okay. So here C1, you rename it to compressor, and after you type, you have to press enter. Okay, then only it will change. If you don't press enter, then the name will not be changed. Okay, so here it is compressor, and number one is inlet air. Okay, that is initial air. Okay, and number two is compressed air. Number two is compressed air. Okay, so here no need to change energy flow. Okay, let it be E1. Okay, so now what you have to do, you have to go to inlet air. Okay, inlet air. So here you have to select the temperature. Okay, let it be 25 degrees Celsius. And you have to select the pressure. Let it be 1 atmosphere. Okay, and mass flow. You have to randomly initialize some value for mass flow. Okay, here I am giving 150, 150. Okay, after pressing 150, you have to press enter. Okay. Now before it was red in color. Now it changed to blue color. It means that the compressor is working good. Okay. So if it is in red, it means that either the simulation is running or the system is not working. Okay. If it is in blue color, then only it means that the simulation is working. Okay. So now after giving temperature at 25 degrees Celsius, pressure at 1 atmosphere, mass flow at 150 kg per second, you have to go to excuse me. You have to go to compound amounts. Okay. So in these compound amounts, if you see the mole fraction, one is distributed equally among all the 5 components. Okay. But it is not required for us. So what you have to do is you have to click on clear. You have to click on clear and you have to give nitrogen. You know very well that nitrogen contains 79% nitrogen. Sorry, air contains 79% nitrogen and 21% oxygen by mole. Okay, so I am typing 0.79 for nitrogen and 0.21 for oxygen, and you have to click on accept. Okay, so now the inlet air is ready. Next, you have to click on compressor. Next, you have to click on compressor. Then compressor, you have to feed two values. First value is outlet pressure. Okay, first value is outlet pressure. Okay, outlet pressure, we are increasing the pressure from 1 atmosphere in inlet air to 17 atmosphere in compressed air. Okay, so here you have to press 7, you have to type 17 and press enter. Okay, so it means that the pressure is increased from 1 atmosphere to 17 atmosphere. Okay. And second one, you have to type the adiabatic efficiency of the compressor. Okay. The normal value of the adiabatic efficiency of compressor is 85%. Okay. So here you give 85%. Okay. So now if you see the compressed air, you can see the pressure is increased to 17 atmosphere. Okay, and the temperature increased from 25 degrees Celsius to 445.82 degrees Celsius. Okay, and the flow rate remains as such as 150 kg per second. Okay, and if you go to compound amount, you can see the composition, the nitrogen at 79% and oxygen at 21%. Okay, and here that now we are going to add the second compound is the reactor, combustion chamber. Okay, but here you cannot directly give to combustion chamber because as I told you before, in combustion chamber, the reaction occurs between compressed air and natural gas. Okay, so here in DWSIM, you cannot mix compressed air and natural gas directly into the reactor. For example, the bottom menu, you go to reactor and we are going to use Gibbs reactor. Okay. If you see the configuration of Gibbs reactor, it is having one inlet and two outlets. Okay, one inlet material stream and two outlet material streams. Okay. So here you cannot add fuel now. Okay, because there is only one inlet stream. Okay, so for that what I am doing, so before sending to reactor, I am mixing, okay, I am mixing this compressed air and natural gas. Okay, so when I delete reactor, only the reactor will be deleted. Okay, the remaining streams will be there. So you have to select each stream and delete them. Okay, so now I am going to mix compressed air and compressed natural gas. Okay, for that in the bottom menu, you have to select mixers or splitters and choose this stream mixer and place it here. And place it here. Okay, so now the compressed air is entering into mixer. Okay, so this mixer, I am calling it as gas mixture. Okay, this mixture, I am renaming it as gas mixture. And stream 4 is nothing but compressed natural gas. Okay, the stream 4, I am renaming it as compressed natural gas. Okay, and it is checking the temperature. The temperature remains same. Okay, temperature remains same, 25 degrees Celsius, but it enters at the pressure of 62 atmosphere. It enters at the pressure of 62 atmosphere. Okay, so now you have to fix the mass flow for compressed natural gas. Okay, now you have to do a small calculation. Okay, if you see the calculation states that power plant efficiency is equal to power output multiplied by 100 divided by energy input by fuel. Okay, so for the power plant which I considered, efficiency is 53.7%. Okay, and for this 53.7% power plant efficiency, the power output is 111.325 megawatt. Okay, multiply by 100 divided by. So the energy input by fuel is mass flow of natural gas multiply by calorific value of natural gas. calorific value of natural gas. Okay. So here, if you see, the 53.7 is equal to 111.325 multiplied by 100 divided by. Actually, we have to calculate only the mass flow of natural gas. Okay, and the calorific value of natural gas is 46.7 megajoule per kilogram. So from here, I am calculating mass flow of natural gas. Okay, the calculation 111.325 multiplied by 100 divided by 53.7 multiplied by 46.7. Okay, so here it is megajoule, right? So this megajoule is nothing but megajoule per second. Here it is megawatt. Okay, power output is megawatt. So the megawatt is nothing but megajoule per second. And the unit of 46.7 is megajoule per kilogram. Okay. So if you see, if you go to the calculator and do this calculation, so 111.325 multiplied by 100 divided by 53.7 multiplied by 46.7. So something is wrong here. What is the mistake? Mass flow. So to be I think I have done some mistake in calculator. Let me check again. 1.325 multiplied by 100 divided by 53.7 multiplied by 46.7. Oh, actually, mass flow rate of gas should come here as 4.4 kg per second. Okay. Check with my calculation. What is the mistake I have done? Okay. You see, it is 1.325, 46.7. Everything is right only. I am getting 4.44 here. Megawatt is megajoule per second. Okay. That actually it should be 4.4 kg per second only. I don't know why I am getting like this. You please check the calculation, okay? But it will come 4.4 kg per second only. Okay, see here. Here I have done the calculation and according to my report, it is 4.4 kg per second only. Okay, so okay, no problem. So go back to DWSIM. Okay, and type here 4.4 kg. The mass flow of natural gas is 4.4 kg per second. Okay, so press here 4.4 kg per second and press enter. So now though it is done, and next you go to compound amount and again see here the mole fraction one is distributed among all the components. So here you have to clear. Here I am assuming the natural gas contain 90% methane and 10% CO2. Okay, so I am giving 0.9 for methane and 0.1 for CO2. Okay, then click on accept. Then click on accept. Okay, so now the compressed natural gas is given. So now we have to click on gas mixture. So here, if you see, you have to set, is it inlet minimum? Inlet minimum means minimum value of compressed air and compressed natural gas. Okay. And inlet average means average of temperature and pressure of compressed air and compressed natural gas. And inlet maximum means the maximum value between temperature and pressure of compressed air and compressed natural gas. So here into the combustion chamber, the stream enters at the pressure and temperature of compressed air only. Okay, so here I am setting inlet minimum because here the compressed air enters at 17 atmosphere and here the compressed natural gas enters at 62 atmosphere. So since the reactor receives the stream at the pressure of compressed air, I have selected inlet minimum here. Okay, so then next now I can add reactor. Okay, go to the reactors in the bottom menu and select Gibbs reactor, drag it and place it here in DWC. Okay, so now just you can click the left click and you can move the diagram from left side to the right hand side. Okay, and if you double click, the size will become big. Okay, if you click double click, the size will reduce. Okay, so these options are there in DWC. Okay, so now next, so this is the combustion chamber. Okay, so now I am renaming this as combustion chamber. Okay, and I want to rename this stream number 5. Okay, the stream number 5, I want to rename it as feed gas. Okay, and the stream number 7, I want to rename it as combustion gas. Okay, here I am renaming it as combustion gas. And actually from the reactor, there are two streams coming out. Okay, one is gas stream, other one is liquid stream. So according to our reaction, after the combustion of methane, you get CO2 and H2O in the form of gas only. Okay, so the stream 8 liquid, it is not applicable for our system. But for that, if you delete, the simulation will not work. So you have to keep it and you have to rename it as liquid. And since it is not active in our system, I am renaming it as liquid dummy. Okay. And then also this energy E2. Okay. No need to rename because let it be E2. Okay. And now see combustion chamber is in red color. It means that it requires some attention. Okay, so click on this combustion chamber. Then you have to check what are the things you have to do. Okay, here if you see the inlet stream is feed gas, outlet stream is combustion gas, second outlet stream is liquid dummy, energy stream is E2. Okay, the calculation mode, you have to click on define outlet temperature. Okay, actually the outlet temperature will be around 1200 to 1300 degrees Celsius. Okay, so I am randomly typing 1250 and press enter. Okay, then click on compounds and type what are the compounds involved in the reaction. So here air means nitrogen and oxygen. Okay, so natural gas means methane and carbon dioxide. Okay, and the products are carbon dioxide and water. So all these 5 components are involved in this reaction. So select all the 5 components. Okay, no need to go for elements and convergence. Okay, these are not required. So you directly come to parameters. Okay, so here after setting it as 1250 degrees Celsius, again you have to change it to adiabatic. Okay, now what you have to do, on the top, if you see below the results, you can see the solve button. Okay, you have to click on solve button. Okay, click. So when I click on solve button, the reactor becomes green color. It means that simulation is running. Okay, it takes some time. Normally the simulation takes some time depending upon the process conditions. Okay, so now we have to wait until the reactor becomes blue color. Now see the reactor becomes blue color. Okay, so now if you see the click on combustion gas, you can see we have given the temperature as 1250 degrees Celsius, right? But it is not. The actual temperature is 1298.98, almost 1300 degrees Celsius. Okay. And as I told you, since the combustion reaction is isobaric, the combustion gas is leaving at the same pressure as compressed air, which is at 17 atmosphere. Okay, and here for air, I have given 150 kg per second. And for compressed natural gas, I have given 4.4 kg per second. So these two mix it together and the mass flow becomes 154.405 kg per second. Okay, so next you have to go to compound amount. And in the compound amount, you have to see the percentage of oxygen. So this is the main role of chemical engineer in this power plant. Okay, so this oxygen percentage should be 13. This oxygen percentage in the combustion gas should be 13. That is 0.13. Okay, but here it is 0.1235. Okay, so now this oxygen composition has to be increased to 0.13. How you can increase the oxygen content? If you increase the compressed natural gas flow, then oxygen will not increase. Okay, so if you increase inlet air mass flow, then it will increase. Okay, so now I am randomly increasing it to 160. Okay, when I click on 160, again the reactor become green color. It means that simulation is running. Okay, so you have to wait for the final calculation. See here, now we will see the oxygen in combustion gas. Okay, combustion gas compound amount, it is 12.87. Okay, it has increased. Okay, now no need to increase 10. Okay, now let me increase it to 165. Okay, now let me increase it to 165 and see the percentage of oxygen in combustion gas. So actually you may ask why the oxygen in combustion gas should be 13. Why not 11? Why not 12? Or why not 14? Actually, if the combustion gas is more than 13%, if the oxygen in combustion gas is more than 13%, then there will be a emission of NOx, carbon monoxide, etc. Okay, and if the oxygen in combustion gas is less than 13%, then the efficiency of gas turbine will reduce. Okay, so because of these two reasons only, we are maintaining the O2 in combustion gas at 13%. See here, it is 0.1311. Okay, it should be between 13 to 14%. Okay, so now it is 13.11, which is between 13 to 14%. So now up to here, the simulation is running perfect with the inlet air mass flow of 165 kg per second and the inlet mass flow of compressed natural gases 4.4 kg per second. So now the third compound. Who is the third compound? What is the third compound? It is gas turbine. Correct. So the gas turbine is available in the down menu of pressure changes, and click on this turbine and place it here. Okay, see here, now the turbine is ready. Okay, now click on this gas turbine and rename it. And rename it as gas turbine. Okay, and rename the stream 8. This is called exhaust gas. This is called exhaust gas. Okay, and let it be E3. Okay, so now again you go to gas turbine. Okay, in gas turbine, the already again I told you here this is isentropic process. So the pressure will decrease from 17 atmosphere to 1 atmosphere. So here already the outlet pressure is 1 atmosphere. Okay, adiabatic efficiency is showing it as 75%, and normally this value is 85%. Okay, so change it 75 to 85 and press enter. Okay, so now the gas turbine is ready. Okay, now the simulation of total Brayton cycle is completed. Okay, so this is the complete Brayton cycle. Okay, as you know already, it has three main components. One is compressor, second one is combustion chamber, and the third one is gas turbine. Okay, see here. So here the gas turbine produces 131.35 megawatt, out of which 72.45 megawatt is used by the compressor. Okay, so to calculate the total power output from Brayton cycle, you have to use energy mixer. Okay, if you select the mixer splitter from the down menu, and there is a compound called energy mixer. This energy mixer is available only in this version of DWSIM 8.4.1. Okay, so because of this only, I insisted you to download only DWSIM 8.4.1 in the beginning of this video. Okay, so now the energy mixer is here. So click on energy mixer and rename it. Rename it as energy mixer. Okay, rename it as energy mixer. So now there is an energy mixer. Okay, you have to select the inlet. You have to select the inlet. Inlet is E3. Okay, another inlet is E1. Okay, one inlet is E3. E3 is power generated from the gas turbine. Okay, now another inlet is E1, that is power to compressor. But this one you should not add, right? So we have to subtract the power generated by the gas turbine and the power generated required for the compressor. Okay, so for that, what you have to do, you have to make one specification block. Okay, you have to make one specification block. Okay, for that in the down menu, you have to select logical block. So from the logical block, there is a specification block. Okay, so you insert this specification block between E1 and energy mixer. Okay, so now what you have to do, click on the specification block. So no need to rename this specification block. Okay, as it is not a major component. Okay, the source object is compressor, and source property is energy flow. Sorry, it is not compressor, it is E1. Okay, source object is E1 and the source property is energy flow. And the target object is energy mixer. Target object is energy mixer, and the target property is, okay. So here what you have to do, to get the total power output from Brayton cycle, you have to subtract power generated from gas turbine minus power required for compressor. Okay, so for that, since it is minus, you have to use minus X. X is the power required for the compressor. Okay, so when you type minus X, and press enter. Okay, and press enter. So now if you see, the power required from compressor has come. Okay, so now here you have to introduce one energy stream after the energy mixer. Okay, because the E4 is the total power output from the Brayton cycle. So here the E4 is equal to E3 minus E1. Okay, now we have to click on energy mixer and press solve button. Okay, now it will calculate. Now the calculation is going on. Again, the simulation is running, so it takes some time. Okay. Okay, I think there is some mistake here. So I think we have to introduce another energy stream before energy mixer. Okay. And you have to connect this specification block to E5. You should not connect it to energy mixer. You have to connect it to E5 and specification property. You have to select energy flow. Okay, then I will click solve. And I have to click on this energy mixture and select this E5. Okay, so select this E5. So now click on solve. Okay, if you click on solve, see here, yes, this is the mistake. Okay, we have to place another energy stream. Okay, before energy mixture, between energy mixture and specification block. So here, if you see 131.35 minus 72. It is not calculating. So sometimes what happens when compared to this energy mixture, it will not work sometimes. Okay, so what you have to do? So I am saving this file. Okay, I am saving this file as simulation of Brayton cycle. Save this file. Okay, then close this. Close this file. Then again go to file. Okay, click on open file. So select this simulation of Brayton cycle. Now if you click on energy mixer and click solve, now the calculation will work here. Sometimes it happens like this. Okay, not all times. Sometimes it happens like this. So now if you see the power generated by the gas turbine is 131.35 megawatt and the power used by the compressor is 72.45 megawatt. And after subtracting the power generated by the gas turbine and the power used by the compressor, the total power output from the Brayton cycle is 58.90 megawatt. Okay, so now you can ask me, teacher, you told me the power output is 111.325 megawatt, but now it is only 58.90 megawatt. Actually, this power output is only from Brayton cycle. Okay, but that power 111.325 megawatt is from combined cycle, which includes Rankine cycle also. Okay, so this is the thing. If you have any doubt, please ask me anytime. Okay, so this is the end of this video. So I hope you understand everything. Please practice well. And if you have any doubt, please ask me anytime. Okay. Thank you very much.